Something unprecedented is about to happen. An object formed around a star that died long before our Sun existed is approaching its closest point to Earth on December 19th, 2025, and in just the last 72 hours. New data from Hubble, James Webb, and XMM Newton has forced scientists to quietly reconsider what 3I Atlas actually is. This object is emitting X-rays. Its color has shifted from red to green faster than any known comet. Its chemistry shows methanol levels that do not fit existing comet models. And its path through Jupiter's gravity was disturbingly precise. Tonight, we examine the data driving a growing scientific divide, including why Avi Loeb assigns a 30 to 40% chance this is not natural at all. If you value careful science over headlines, like and subscribe. Now, let's begin. December 14th, 2025. 3I Atlas is moving through the inner solar system at a speed of roughly 250,000 kilometers per hour. That places it among the fastest objects ever measured passing through our local cosmic environment. To understand that speed in familiar terms, an object moving this fast would cross the distance between New York and Los Angeles in well under a minute. It would travel from Earth to the Moon in about 90 minutes. This is not the slow, gradual motion of an asteroid long bound to the Sun. This is the velocity of an object that is not gravitationally at home here, one that is passing through rather than settling in. On December 19th, 2025, 3I Atlas will reach what astronomers call its closest approach to Earth. Even then, it will remain far away by everyday standards. At a distance of approximately 270 million kilometers, that is close to 1.8 times the average distance between Earth and the Sun. The space between us and the object is vast. Hundreds of Earths could fit comfortably in that gap. There is no danger to our planet, no collision risk, no hidden threat. Space agencies, including NASA, have repeated this point clearly and consistently. But distance is a relative concept in astronomy, especially when discussing objects that originate outside our solar system. The nearest star to the Sun, Proxima Centauri, lies more than 4 light-years away. 3I Atlas has traveled at least that far, likely much farther. Before entering our view, for billions of years it moved through interstellar space, a region defined by extreme cold, low density, and near total darkness. Now, for a short window of time, it is close enough for detailed study using instruments that did not exist even a few decades ago. That brief overlap between its path and our technological capability is what makes this moment unusual. The timing adds another layer. December 19th coincides with a new moon. With no moonlight in the sky, ground-based telescopes will operate under darker conditions, allowing fainter details to be detected. For observational astronomy, this matters greatly. Reduced background light improves clarity, contrast, and sensitivity. As a result, observatories across the world are preparing for this date with careful coordination. Space-based instruments have already begun repeated observations. The Hubble Space Telescope has turned toward 3I Atlas several times and is scheduled to do so again. The James Webb Space Telescope continues to collect infrared data. On the ground, major facilities in Chile, Hawaii, and the Canary Islands are aligning their schedules and instruments. Rarely has so much observational capability been focused on a single object within such a narrow span of time. This effort is driven by a growing realization that the object is not behaving as expected. When 3I Atlas was first identified on July 1st, 2025, by the Atlas Survey Telescope in Chile, Astronomers immediately recognized that it was not native to our solar system. Its path through space did not follow a closed orbit around the Sun. Instead, it traveled along a hyperbolic trajectory, meaning it is moving too fast for the Sun's gravity to capture it. Objects on such paths come from elsewhere and will continue onward after passing through. This alone placed 3I Atlas in a rare category. There have been only 2 confirmed interstellar visitors observed before. The first, detected in 2017, was Oumuamua, an elongated object whose unusual shape and motion sparked widespread debate. The second, observed in 2019, was Borisov, a more familiar-looking comet that behaved much like comets formed in our own system. 3I Atlas is the third confirmed case. The number 3 in its name reflects this, while the letter I stands for interstellar. Based on these precedents, researchers expected a general pattern. As it approached the Sun, the object would warm. Frozen materials near its surface would turn directly from solid to gas, a process known as sublimation. This gas would carry dust outward, forming a surrounding cloud called a coma, and eventually, one or more tails extending away from the Sun. For several months, observations appeared to confirm these expectations. Images from Hubble showed a diffuse, teardrop-shaped coma surrounding a brighter central region. Infrared measurements from James Webb identified common cometary substances, including water vapor, water ice, carbon dioxide, carbon monoxide, and carbonyl sulfide. These are typical components released when icy bodies are heated by starlight. While the object was clearly different from comets formed near our Sun, its overall behavior fit within established comet models. That sense of familiarity began to break down in late October, when 3I Atlas reached perihelion, its closest point to the Sun. At a distance of about 203 million kilometers, this is normally the stage when comet activity increases sharply. Stronger sunlight should drive more intense sublimation, producing brighter comas and longer, more visible tails. Models predicted noticeable changes in brightness and structure following this close pass. Instead, the opposite occurred. Images taken after perihelion, released in early November, showed a compact source of light with no clear, extended tail. The coma was still present, but it appeared similar to how it had looked months earlier. There was no dramatic expansion, no sudden surge in activity. For an object assumed to be rich in volatile ices, this was difficult to explain. If mass loss was occurring as expected, its visual appearance should have changed significantly. The lack of such change created confusion and prompted re-examination of earlier assumptions. The prevailing explanation within planetary science remains cautious. 3I Atlas likely formed in a different stellar environment, with different temperatures, pressures, and chemical abundances. Its internal structure may be denser or layered in ways that slow down gas release. Its surface may be coated with materials that insulate underlying ice. Any combination of these factors could alter how it responds to heating. From this perspective, the object is unusual but still natural, and the gaps in our models reflect limited experience with interstellar material rather than anything more exotic. Alongside this conservative view, another interpretation has gained attention. Avi Loeb, a theoretical astrophysicist and former chair of Harvard's astronomy department, has argued that certain features of 3I Atlas deserve closer scrutiny. Since the object's discovery, he has cataloged a set of behaviors he describes as anomalies, meaning they do not fit neatly within standard cometary explanations. As of his most recent analysis, he identifies roughly 10 such points. he emphasizes that the object is most likely natural. But he assigns a probability on the order of 30 to 40% that it could have a technological origin. This statement has been widely discussed and often misunderstood. Loeb is not claiming that 3I Atlas is an alien spacecraft. He is arguing that, given the data available so far, an artificial explanation cannot be ruled out with high confidence. He calls for more observation and more openness to unconventional possibilities, particularly when dealing with objects that fall outside well-tested categories. Many scientists strongly disagree with this framing. Critics argue that unusual behavior does not imply artificial origin, especially when the sample size of known interstellar objects is extremely small. With only 2 prior examples, expectations are poorly constrained. Astronomers such as Jason Wright at Penn State have published detailed responses showing how each cited anomaly could arise through natural physical processes. From this perspective, invoking technology introduces unnecessary assumptions when simpler explanations remain viable. This disagreement reflects a broader question in science about how to approach the unknown. One approach favors minimal assumptions and established mechanisms, adjusting models gradually as new data appears. Another approach emphasizes openness to rare or transformative possibilities, even if they challenge current frameworks. 3I Atlas sits at the intersection of these philosophies, not because of any single observation, but because of the growing list of measurements that resist easy classification. What stands out most at this stage is not the debate itself, but the pace at which new information is arriving. Each day brings additional observations from different wavelengths and instruments. In the last 72 hours alone, the European Space Agency has released X-ray images captured by the XMM Newton Observatory. Optical measurements from the Gemini North Telescope in Hawaii have documented changes in color over time. Spectroscopic analysis has revealed chemical signatures that do not align cleanly with existing comet models. These findings add detail to the picture, while also increasing uncertainty. The coming days matter because December 19th represents the best opportunity to collect high-resolution data while the object is still relatively close and favorably positioned. After this window, 3I Atlas will continue outward, passing near Jupiter in March of 2026 before leaving the inner solar system entirely. It will not return. Whatever information can be extracted must be gathered now. This leads to a central question. What do we actually know at this point? Based strictly on observation, why do some researchers feel more unsettled now than they did months ago? The answers begin with a form of light that human eyes cannot see, but modern instruments can detect. For the first time, we are observing X-rays coming from 3I Atlas. These are high-energy photons emitted in quantities that are difficult to reconcile with standard cometary processes. The object is producing invisible radiation that, until very recently, we had no way to measure at all. On December 3rd, 2025, the European Space Agency directed one of its most sensitive space instruments toward 3I Atlas. The observatory used for this task was XMM Newton, a telescope designed to detect a form of light that human eyes cannot see. Unlike optical telescopes, which capture the visible colors of stars and planets, XMM Newton observes X-rays. These are high-energy photons associated with the most extreme environments in the universe. X-rays are typically produced where temperatures reach millions of degrees, where particles collide violently, or where matter is falling into dense objects like neutron stars or black holes. They are not the kind of radiation one expects from a small, cold body made of ice and rock. For 20 continuous hours, XMM Newton tracked 3I Atlas as it moved through space. When the European Space Agency released the processed image on December 12th, It revealed something striking. At the center of the frame was a concentrated region of X-ray emission, shown in red through false color processing. This coloring does not represent visible light. It is a translation that allows scientists to visualize energy levels that would otherwise remain invisible. Surrounding this central glow were faint gradients fading into purple and blue, marking regions where the X-ray signal weakens and then disappears into background space. The image showed a clear boundary between active interaction and near emptiness. At first glance, the result raises an obvious question. How can a comet produce X-rays at all? Comets are generally cold. They are remnants of planetary formation, composed mostly of frozen gases mixed with dust and rock. They do not generate heat internally, and they do not host violent processes like those found near stars. The explanation lies not within the comet itself, but in how it interacts with its surroundings. As 3I Atlas travels through the solar system, sunlight warms its surface. Frozen materials near the surface turn directly into gas and flow outward, forming a cloud known as the coma. This gas includes water vapor, carbon dioxide, methanol, and other volatile compounds. These particles are electrically neutral. They drift outward slowly, expanding into space without carrying an electric charge. The space between the planets, however, is not empty. It is filled with the solar wind, a continuous stream of charged particles flowing outward from the sun. This wind moves at hundreds of kilometers per second and contains protons, electrons, and ionized atoms of heavier elements. It also carries the sun's magnetic field throughout the solar system. When this stream of charged particles encounters the neutral gas released by a comet, a specific type of interaction occurs, known as charge exchange. In a charge exchange event, an ion from the solar wind captures an electron from a neutral atom or molecule in the comet's coma. The captured electron initially occupies a high-energy state. As it settles into a lower energy configuration, it releases energy in the form of X-rays. This process happens repeatedly, billions of times across a large region of space. The result is a diffuse halo of X-ray emission that can extend far beyond the visible coma seen by optical telescopes. This mechanism is well understood. It was first confirmed in the mid-1990s when comet Hyakutake was unexpectedly detected in X-rays. At the time, the discovery surprised astronomers, but it quickly became clear that charge exchange was responsible. Since then, X-ray emission has been observed from several comets within our solar system. In that sense, the detection of X-rays from 3I Atlas confirms that it is releasing gas and interacting with the solar wind in a familiar way. What makes this observation valuable is not the presence of X-rays alone, but what their strength and structure can reveal. X-rays are especially sensitive to certain elements that are difficult to detect at other wavelengths. Compounds containing carbon, nitrogen, and oxygen often participate efficiently in charge exchange reactions. Some of these species produce weak signals in visible or infrared light, making them hard to measure directly. By studying the X-ray spectrum, scientists can infer the presence and relative abundance of these otherwise hidden components. During the XMM Newton observation, 3I Atlas was roughly 282 to 285 million kilometers from the spacecraft. The observatory used its most sensitive detector, known as the EPIC-PN camera, to collect as many X-ray photons as possible. Early analysis shows emission features associated with carbon, nitrogen, and oxygen. These are exactly the elements expected from charge exchange between solar wind ions and cometary gas. However, the relative strengths of these signals carry information about the composition of the gas itself. and that information is still being carefully analyzed. XMM Newton was not the first X-ray telescope to observe 3I Atlas. Less than a week earlier, another mission had already focused its attention on the object. The Japanese Aerospace Exploration Agency operates a satellite called X-RIMS, short for the X-ray Imaging and Spectroscopy Mission. Between November 26th and November 28th, the mission conducted what astronomers call a target of opportunity observation. This means the normal observing schedule was interrupted to study an object considered unusually important. For 17 hours, X-RISM tracked 3I Atlas as it moved across the background stars of the constellation Virgo. During that time, the spacecraft adjusted its position repeatedly, making course corrections roughly every 3 hours to keep the object centered in its field of view. This careful tracking allowed the team to build up a deeper exposure than would otherwise have been possible. The results added a new dimension to the picture. X-RISM detected a faint X-ray glow extending about 5 arc minutes from the comet's position. When translated into physical distance, this corresponds to roughly 400,000 kilometers. This means the X-ray emitting region surrounding 3I Atlas spans a volume larger than the distance between Earth and the Moon. Rather than a compact point of emission, the data suggests a broad, extended halo where cometary gas and the solar wind are interacting across an enormous region of space. The X-RISM team emphasized caution in their initial report. Extended structures can sometimes arise from instrumental effects or background variations, and detailed analysis is required to confirm that the signal is real. Even so, the detection is difficult to dismiss. If confirmed, it implies that 3I Atlas is releasing a substantial amount of gas, far more than what is immediately obvious from optical images alone. These findings drew commentary from Avi Loeb, who noted that the size and shape of the X-ray halo appear consistent with gas plumes previously detected by the James Webb Space Telescope and by NASA's SPHEREX mission. In this respect, the X-ray data supports the idea that 3I Atlas is behaving like a natural comet. If the object were artificial in nature, its interaction with the solar wind might look very different. Instead, the observed X-rays follow patterns predicted by well-established physics. At the same time, Loeb highlighted an important limitation. While X-rays reveal what happens when gas interacts with the solar wind, they do not show the source of that gas directly. The nucleus of 3I Atlas remains unresolved. It is too small and too distant for even the most powerful telescopes to image clearly. Scientists can observe the effects of outgassing, measure the composition of the escaping material, and estimate how much is being released. What they cannot yet see is the structure or mechanism responsible for producing that gas. An analogy helps clarify this gap. Imagine observing a distant industrial facility from far away. You see a plume rising into the air. You analyze the smoke and determine its chemical makeup. You estimate how much material is being burned based on the size and density of the plume. All of this confirms that something inside the facility is producing the smoke. What it does not tell you is exactly what fuel is being used. Without seeing inside, multiple explanations remain possible. 3I Atlas presents a similar situation. The X-ray observations confirm active interaction with the solar wind. They reveal the presence of carbon, nitrogen, and oxygen-bearing compounds in the gas. They show that this gas extends far into space. What they do not yet reveal is the fundamental nature of the object producing it. It could be a largely pristine body, preserving material from its birth around another star. It could be a heavily processed remnant, altered by cosmic rays and radiation during a long journey through interstellar space. Or it could represent a category we do not yet fully understand. The prevailing scientific view remains grounded in natural explanations. Charge exchange X-rays are exactly what theory predicts for a comet releasing gas into the solar wind. The observed intensities and spectral features do not require exotic physics. There is no single measurement that demands a technological interpretation. At the same time, the ability to observe 3I Atlas across this wavelength opens new opportunities. Subtle differences in how gas is produced or released could leave fingerprints in the X-ray data as analysis continues. What stands out is the broader context these observations create. For the first time, humanity is studying an interstellar object across nearly the entire electromagnetic spectrum. Visible light reveals dust and structure. Infrared light uncovers molecular composition. Ultraviolet observations track ionized gases. Radio measurements probe large-scale features. Now X-rays illuminate the energetic boundary where material from another star system meets the solar wind of our own. Each wavelength offers a different perspective, and together they form the most complete picture ever assembled of an interstellar visitor. The X-ray investigation is ongoing. As 3I Atlas approaches its closest point to Earth on December 19th, additional observations are planned. The data being collected now will take months to fully analyze. In parallel, other questions continue to circulate. Are there additional wavelengths that deserve closer attention? Are there signals that have not yet been searched for? This leads into one of the more controversial suggestions associated with the object. Avi Loeb has repeatedly argued that it would be worthwhile to listen for radio signals, particularly near the hydrogen line frequency of 1,420 MHz. This frequency is well known in astronomy and is associated with the famous WOW signal detected in 1977. Loeb has noted a rough alignment between the sky position of 3I Atlas and the region from which that signal appeared to originate. He does not claim a connection, but he considers the coincidence interesting enough to justify a targeted search. So far, radio observatories such as the Allen Telescope Array and the Green Bank Observatory have reported no unusual emissions from 3I Atlas. The radio spectrum remains quiet. Supporters of continued observation argue that silence does not resolve the question, only that no signal has yet been detected. What can be stated with confidence is this: 3I Atlas is emitting X-rays. Those X-rays arise from charge exchange interactions that are well understood. The extended halo indicates active outgassing, and the spectral features point to gas containing carbon, nitrogen, and oxygen. All of this fits within the framework of a natural interstellar comet. None of it conclusively proves that interpretation beyond doubt. The invisible light has revealed part of the story, but not all of it. As attention shifts back to what optical telescopes have been recording, another puzzle comes into focus. 3I Atlas has not only changed in brightness and activity, it has changed in color, and that change points to processes that even the X-ray data cannot fully explain. In late August of 2025, Gemini South in Chile captured one of the first detailed color images of 3I Atlas. In those early views, the coma and the region near the nucleus looked distinctly red. It was not the warm red people associate with sunsets. It was a colder, rust-like red, the kind often linked to surfaces rich in complex carbon compounds that have been changed by long exposure to radiation. Astronomers noted it as a useful clue, not as a warning sign. Many small bodies in the outer solar system look reddish for the same basic reason. Over very long times, high-energy particles, often called cosmic rays, can strike surface ices and simple organics and slowly turn them into darker, redder material. That interpretation fit the larger context. 3I Atlas is an interstellar object. Before it entered our system, it likely spent an extremely long time in interstellar space, where it would have been exposed to background radiation without the protection of a thick atmosphere or magnetic field. A red surface is one of the expected outcomes for an icy body that has been processed in that way. Then the color changed in a way that was hard to ignore. On November 26, 2025, Gemini North in Hawaii used its Gemini multi-object spectrograph to image 3I Atlas again. By then, the object had already passed perihelion, its closest point to the Sun, and it was moving outward. In simple terms, it was leaving the region of strongest heating and should have been trending toward lower activity. The coma still looked fairly compact, and the tail was not especially dramatic, but the color balance was different. In the processed composite, built from exposures through blue, green, orange, and red filters, the coma showed a clear greenish glow. This was not a slight tint that required imagination. It was a visible shift in how the coma was emitting light. A green coma has a known explanation in comet science. Many comets show a green glow close to the nucleus when they are active. The most common source is a molecule called diatomic carbon, meaning two carbon atoms bonded together. In scientific writing, it is often labeled as C2. When sunlight energizes these molecules, they can re-emit part of that energy as visible light. And a strong part of that emission falls in the green range. The result is a kind of natural fluorescence. It is not paint, and it is not a filter effect. It is light produced by specific molecules in the coma. Diatomic carbon is not rare in comet comas. It has been detected in many comets in our own solar system, especially when they become active closer to the Sun. The key question for 3I Atlas is timing. In late August, it looked red, and the green signature was not dominant. By late November, the green had become prominent. That suggests that something changed in the coma chemistry, or in what the coma was exposing. Between those dates, the simplest explanation connects to heating during perihelion. 3I Atlas reached perihelion on October 29, 2025, at a distance of about 1.36 astronomical units from the Sun. Based on early orbital solutions, that perihelion passage was the moment of strongest solar input during its visit. Heat does not affect an icy body all at once. It can take time to move through layers, and it can expose new material gradually. As fresh layers warm, new gases can be released, and new chemical pathways can become active in the coma. Diatomic carbon itself usually does not come straight from the nucleus as a stable ice. In many comets, it is produced after release, when sunlight breaks apart other carbon-bearing molecules in the coma. Those original molecules are often called parent molecules, and diatomic carbon is then called a daughter species, meaning it is made later as a secondary product. One proposed parent is tricarbon, often written as C3. Ultraviolet light can break tricarbon into smaller fragments, including diatomic carbon. Other organic molecules can also lead to the same result. Which pathway dominates depends on the object's specific chemistry, and that chemistry can vary strongly from comet to comet. So the green glow is evidence of continuing change, not a one-time event. It suggests the coma is still being supplied with fresh material, and that sunlight is still actively reshaping that material into new products. Even if the visible coma looks compact, chemical evolution can continue inside it. A delayed green signal, appearing weeks after perihelion, is consistent with the idea that the most important releases may have begun at perihelion but became easier to detect later as daughter species built up, spread through the coma, and reached emission levels that stand out in color images. This color shift is also informative because it hints at layering inside the object. The red seen in August likely reflected the surface that had been exposed the longest to radiation in interstellar space. In planetary science, One common label for radiation-made reddish organics is tholins. Tholins are not a single substance, but a family of complex carbon and nitrogen-rich materials formed when simple molecules are irradiated, often in cold conditions. They are known from many places in our solar system, including Titan and Pluto, and are thought to be widespread on small icy bodies. A red, tholin-rich surface is consistent with an old, radiation-processed outer layer. As the Sun warmed 3I Atlas, that outer layer could begin to erode, crack, or shed, revealing fresher material underneath. Fresher here does not mean young. It means less altered by radiation. Material below the surface can be shielded for long periods, preserving more of its original ice and organic mix. If those deeper layers contain parent molecules that can produce diatomic carbon once released, then the coma can shift from looking red-dominated to green-dominated as activity changes what is being supplied to the coma. Neuer Lab, which operates the Gemini telescopes, emphasized in its public release that green comas are common in active comets and that the basic mechanism is well understood. In other words, a red-to-green evolution does not require unusual physics. It can be explained by standard comet chemistry and sunlight-driven processes, especially in an object that is experiencing a close stellar passage after a very long time in deep space. At the same time, the observation still matters because it tells us that 3I Atlas is not a simple, uniform chunk of ice. The color evolution implies different materials are becoming visible at different times. That is exactly the kind of behavior scientists hope to track, because it is one of the few ways to learn about an unresolved nucleus. We cannot directly image the nucleus as a detailed object. What we can do is use changes in the coma as indirect evidence of what the nucleus is releasing, and how that release evolves as heating conditions change. Another point is easy to miss if the focus stays on images alone. The green glow does not mean the whole comet is green. It means the coma has enough of the right emitting molecules to affect the color balance in a composite image. The effect can depend on filter choices, exposure times, and how the data is processed, which is why astronomers pair color imaging with spectroscopy. Spectroscopy breaks light into its components and shows which molecules are actually present. In the Gemini observations, the green appearance was consistent with known cometary emission features and with the idea that carbon-bearing fragments were contributing strongly near the nucleus. Avi Loeb has commented on the color change as well, but his framing differs from the mainstream. He notes that 3I Atlas has not looked the same across the full observing period, and he argues that multiple color states could, in principle, be consistent with different surface regions or different components becoming visible at different times. He has raised speculative possibilities, including the idea that an outer layer could behave differently from a typical comet surface. At the same time, he also acknowledges that the standard explanation, natural outgassing followed by sunlight-driven chemistry in the coma, fits the observations well and does not require any artificial interpretation. Across the broader community, the color evolution is generally treated as expected comet behavior under changing conditions. The timing also lines up with what is often seen after perihelion, when activity can continue even as the object moves outward. Cooling is not instant, and internal heat transport can keep feeding gas release for weeks. In that sense, a green coma appearing in late November is consistent with continued processing of material that was activated during the October perihelion passage. The important caution is that consistent with is not the same as fully solved. Interstellar comets are still a new category in practical terms. We have two prior reference points. Oumuamua moved through so fast and was so small that the observational window was limited. Borisov was more comet-like, but still did not provide enough cases to define a full range of what normal should look like for objects formed around other stars. 3. I-Atlas is providing more multi-wavelength data than both of those earlier cases combined. And it is already showing that interstellar objects can shift in ways that challenge simple expectations. This is where the color story connects to a larger theme running through the entire dataset. 3 I-Atlas appears chemically and structurally complex. It shows signs of layered materials and evolving outgassing products. It looks less like a uniform snowball and more like a differentiated body, with outer layers that have been strongly processed and deeper layers that behave differently once exposed. The more it is observed, the more those differences become measurable. And the color is only one piece of that picture. The green glow is tied to carbon chemistry. But carbon is not the only important element in the coma. The most challenging questions now come from what spectroscopy and other measurements indicate is streaming off the object. What molecules are present? What the ratios look like? And why some of those ratios appear unlike anything measured in solar system comets so far. The data that follows moves beyond color and into composition, a chemistry never seen before. When the James Webb Space Telescope first observed 3 I-Atlas in the infrared in early August of 2025, scientists expected a familiar result. They expected water. Water ice is the defining feature of comets. It is what separates them from asteroids. It is the substance that drives cometary activity and creates the bright tails that have captured human attention for centuries. In most comets, water is the dominant volatile. As the object warms, water ice turns into gas, expands into the coma, and drags dust along with it. Water is usually the main signal, both chemically and visually. That expectation was not met. Instead of water dominating the infrared spectrum, James Webb revealed a coma rich in carbon dioxide. The data showed carbon dioxide gas streaming away from the nucleus in quantities far greater than the water signature. When researchers measured the ratio, they found that carbon dioxide was present at roughly 7.6 times the amount of water. This was not a minor variation. It placed 3 I-Atlas among the most carbon dioxide-rich comets ever observed. In typical solar system comets, water is the primary volatile, and carbon dioxide plays a supporting role. In 3 I-Atlas, that relationship was reversed. Water was present, but it was not in control of the activity. This result immediately raised questions about the object's origin. Carbon dioxide ice forms more easily than water ice at lower temperatures, in the outermost regions of a protoplanetary disk, far from a young star. Conditions can favor the buildup of carbon dioxide over water. If 3 I-Atlas formed in such a region around its parent star, it could naturally contain a higher fraction of carbon dioxide. Another possibility involves time rather than place. During a journey lasting billions of years through interstellar space, cosmic rays can slowly break apart water molecules in surface layers. Carbon dioxide may be more resistant to this long-term processing over extreme timescales. This could tilt the balance away from water. The carbon dioxide discovery, however, was only the beginning. As observations continued through August, September, and October, a more detailed chemical inventory emerged. Each new measurement added depth, and each one made the picture more unusual. High in the Chilean desert, the Atacama Large Millimeter Submillimeter Array operates at an altitude of about 5,000 meters. From that height, above much of Earth's atmospheric moisture, it can observe the universe at millimeter and submillimeter wavelengths with exceptional clarity. During late August through October of 2025, ALMA was used to study 3I Atlas at these wavelengths. The goal was to detect molecules that emit faint radiation in this part of the spectrum and to use those signals to infer composition and activity. One of the molecules detected was methanol. Methanol is a simple alcohol molecule made of carbon, hydrogen, and oxygen. It is common in the interstellar medium and has been found in many comets. Its presence alone was not surprising. The quantity was. Measurements indicated that 3I Atlas was releasing roughly 40 kilograms of methanol every second. This was not an isolated burst. It was a steady flow. To put that number in context, methanol typically makes up about 2% of the gas released by a solar system comet. In 3I Atlas, methanol accounted for roughly 8% of the total outgassing. That is about 4 times higher than normal. This placed the object among the most methanol-rich comets ever observed. It was not outside the realm of physics, but it sat at the extreme end of the known distribution. ALMA also detected hydrogen cyanide. This molecule consists of one hydrogen atom, one carbon atom, and one nitrogen atom. Hydrogen cyanide is notable for several reasons. It is toxic to most life on Earth. Yet it is also considered a key precursor in prebiotic chemistry. Under certain conditions, it can participate in reactions that form amino acids and the building blocks of genetic material. It is a molecule that connects chemistry to biology. In 3I Atlas, hydrogen cyanide was detected coming from near the nucleus at production rates between roughly 1/4 and 1/2 kilogram per second. That amount was smaller than the methanol output, but still significant. When scientists compared the methanol production to the hydrogen cyanide production, they found something rare. The ratio between the two was among the highest ever measured in any comet. Only one previously observed comet showed higher values. That object was so chemically unusual that it was classified as anomalous. 3I Atlas now occupies a similar position. Its methanol to hydrogen cyanide ratio places it at the edge of the known comet population. It is not impossible. It does not violate chemistry, but it is uncommon enough to demand attention. There is another layer to the methanol result that has puzzled researchers. In most comets, volatile gases originate mainly from the nucleus. Ice sublimates from the surface or from localized vents and jets, and the coma reflects that central source. In 3I Atlas, the data suggest that methanol is not confined to regions close to the nucleus. Instead, it appears distributed throughout a larger volume of the coma. One possible explanation involves dust grains. As the nucleus releases dust, those grains can carry trapped pockets of methanol ice. As the grains drift away and continue to warm in sunlight, they release their own gas. The result is a more spread out source of methanol, not tied to a single point. Another possibility is chemical processing within the coma itself. Parent molecules released from the nucleus could break apart or recombine under solar radiation to form methanol as a secondary product. This would be unusual, since methanol is normally considered a parent species that survives intact. But unusual does not mean forbidden. A third possibility involves the structure of the nucleus. If 3I Atlas is not uniform, but instead made of regions with different compositions, then methanol-rich zones could be scattered throughout it. As the object rotates and different areas face the sun, outgassing patterns would change. The coma would reflect that complexity. This idea of a heterogeneous nucleus is not radical. Detailed studies of solar system comets, such as the one visited by the Rosetta spacecraft, have shown layered structures, compositional variations, and complex internal geometry. There is no reason to expect an interstellar comet to be simpler. What makes the chemistry of 3I Atlas particularly interesting is the combination of all these findings. High carbon dioxide relative to water, very high methanol output, an unusual methanol to hydrogen cyanide ratio. Signs that at least some volatiles are coming from distributed sources rather than a single surface. Each observation can be explained within established cometary science. Together, they describe an object that sits near the boundary of what our current models are built to handle. Avi Loeb has commented on this chemistry from a different angle. He has noted that some aspects of the detected composition resemble industrial materials on Earth. In particular, he has pointed to reports of nickel detected in the coma without a corresponding amount of iron on Earth. That ratio is common in certain nickel-based alloys used in aerospace engineering. He suggests that, in principle, such signatures could be consistent with manufactured materials. At the same time, he acknowledges that natural processes can also produce unusual elemental ratios, and that the current data do not allow for firm conclusions. The broader scientific response has been cautious. 3I Atlas is clearly unusual, but it comes from another star system. Differences should be expected. The question is whether those differences fall within natural variation or whether they point to something fundamentally different. An analogy helps frame this. Imagine studying animals in one continent your entire career. You learn every species, every pattern, every sound. Then you are shown an animal from a distant continent shaped by a different environment. It looks strange, behaves differently, and does not match your expectations. That does not make it artificial. It makes it unfamiliar. Its differences reflect where it came from. 3I Atlas may be similar. Its chemistry may look wrong only because our reference set is narrow. Every atom in it carries information about conditions around another star. The ratios we find surprising may be normal in that environment. The methanol and hydrogen cyanide detections also carry implications beyond classification. Both molecules are relevant to astrobiology. Methanol can participate in reactions that form more complex organics. Hydrogen cyanide can contribute to pathways that lead to amino acids under the right conditions. Their presence in high abundance means that 3I Atlas carries materials that could, in theory, contribute to the chemistry of life. This connects to the idea known as panspermia, the hypothesis that life, or its precursors, can be distributed through space by comets and asteroids. If interstellar objects commonly carry complex organic molecules, then they could seed young planetary systems as they pass through. Earth itself may have received such inputs early in its history. At the same time, chemistry has no intent. Hydrogen cyanide is also a potent toxin. The same molecules that can support life under one set of conditions can be harmful under another. Context determines outcome. As data processing continues, more chemical details may emerge. Observations from October and November are still being analyzed. Models are being refined. The picture today is clearer than it was weeks ago, but it is still incomplete. What can be said with confidence is that 3I Atlas is chemically rich. It carries a diverse inventory of molecules that reflect its formation, its long preservation in interstellar space, and its current transformation under solar heating. That story is written in carbon dioxide and water, in methanol and hydrogen cyanide, in diatomic carbon and trace metals. By learning to read that story, we are learning about the range of chemistry that exists between the stars. The methanol continues to flow, tens of kilograms every second, a steady release from an ancient object passing briefly through our system. And the question remains unresolved. What else is hidden in that chemical inventory? What other molecules remain undetected? And what will they tell us about the true nature of 3I Atlas? This is the methanol paradox. The methanol mystery deserves closer attention, because this is where the chemistry of 3I Atlas stops being merely unusual and starts challenging some of our most basic expectations about comets. When researchers say that methanol accounts for roughly 8% of the vapor released by this object, they are not pointing to a small deviation. They are pointing to a value that forces a reassessment of how and where this object formed. Decades of comet research within our solar system have established clear patterns. Missions like Rosetta, which spent more than 2 years orbiting and studying comet 67P Churyumov-Gerasimenko, provided an unprecedented close-up view of a cometary nucleus. Instruments directly sampled gas and dust, tracked jets, and followed chemical changes through an entire orbit. Combined with observations of hundreds of other comets from Earth, these datasets built a consistent picture. Water dominates cometary outgassing. Carbon dioxide and carbon monoxide appear in varying amounts. Methanol is present, but usually as a minor component, typically around 2%, occasionally slightly higher in rare cases. The chemistry is rich, but it stays within recognizable bounds. 3I Atlas does not fit comfortably inside those bounds. An 8% methanol fraction is not just high, it suggests that this object formed under conditions different from those that shaped the comets we know. Methanol is not an easy molecule to produce in large quantities. It forms mainly on the surfaces of microscopic ice grains in extremely cold environments. Carbon monoxide molecules settle onto these grains and react step by step with hydrogen atoms. The process requires very low temperatures, a steady supply of atomic hydrogen, and long periods of time. If conditions are too warm, the molecules evaporate. If hydrogen is scarce, the reaction stalls. Methanol abundance is therefore highly sensitive to its formation environment. If 3I Atlas carries 4 times the typical methanol fraction, then its birth environment must have favored that chemistry. Perhaps the protoplanetary disk around its parent star was colder overall, allowing methanol to form efficiently. Perhaps the balance of carbon and hydrogen was different, or the object spent extended time in a region of the disk where methanol production was optimal. We do not yet know which explanation is correct. What we do know is that methanol acts as a chemical fingerprint, pointing back to a stellar nursery that was not like our own. There is another layer to this finding that has received less attention but may be just as important. Observations suggest that methanol in 3I Atlas is not confined to a narrow region close to the nucleus. Instead, it appears spread throughout a larger volume of the coma. One straightforward explanation involves dust grains. As the nucleus releases dust, those grains can carry trapped methanol ice. As they drift away and warm, they release their contents, creating a distributed source of gas. This mechanism fits comfortably within established comet physics. There is, however, a more provocative possibility. Some researchers have raised the idea that methanol might be forming within the coma itself. In this scenario, methanol would not be only a stored molecule released from ice, but a product of chemical reactions occurring in the gas around the comet. This would be unusual. Methanol is generally classified as a parent species, meaning it is thought to survive intact from the nucleus. But unusual does not mean forbidden. The cometary coma is a harsh and dynamic environment. Solar radiation drives photochemistry. Dust grains provide surfaces for reactions. Multiple gas species mix, collide, and break apart. In principle, complex chemistry could occur in real time. If even a fraction of the methanol observed in 3I Atlas is being synthesized in the coma, that would make this object chemically active in a way we have not clearly documented before. It would mean the comet is not just releasing ancient material, but actively creating new molecules as it interacts with the solar environment. This idea remains speculative. The current data do not demand it, and the simpler explanation of methanol-rich grains remains sufficient. Still, the possibility is intriguing enough that it is being taken seriously. These methanol observations connect to a much broader question about the relationship between interstellar chemistry and planetary chemistry. Methanol is abundant in the molecular clouds where stars form. It has been detected throughout the galaxy in regions of starbirth. When those clouds collapse to form stars and planets, methanol becomes locked into icy bodies that later become comets. In that sense, comets are chemical time capsules. They preserve the conditions of stellar birth regions long after those regions have dispersed. If 3I Atlas truly formed around another star, then its methanol content reflects a stellar nursery we have never sampled before. The cloud that produced its parent star may have been richer in methanol than the cloud that formed our sun. That ancient chemistry is now visible to us. Encoded in gas streaming from this interstellar visitor, every methanol molecule detected is a message from a different part of the galaxy, carrying information about conditions that existed billions of years ago. There is something quietly remarkable about this. We invest enormous resources into spacecraft missions designed to explore distant worlds. We imagine future probes that might one day reach other star systems, journeys that would take tens of thousands of years. And yet, here in our own solar system, an object from another star has arrived on its own. It carries material from an alien environment, delivered directly into observational range. The only requirement is that we pay attention while it passes. The methanol paradox also reshapes how we think about chemical diversity across the galaxy. If different stellar environments produce comets with different compositions, then cometary chemistry may vary far more widely than our solar system alone suggests. Some interstellar comets may resemble ours. Others may be dominated by carbon dioxide, like 3I Atlas. Still others may carry molecules we have never seen in any comet before. Considering the vast number of stars that have formed and evolved, the range of possible outcomes is enormous. This raises an uncomfortable but necessary question. How much can we generalize from our own system? For most of human history, we assumed our solar system was typical. The discovery of exoplanets shattered that assumption. We found hot Jupiters skimming their stars, super-Earths with no solar system counterpart, and planets orbiting pairs of stars. Planetary systems turned out to be far more diverse than expected. It is reasonable to ask whether cometary chemistry will follow the same pattern. 3I Atlas suggests that it might. The implications extend into astrobiology. Methanol can participate in chemical pathways that lead to more complex organic compounds. Hydrogen, cyanide, also detected in this object, can contribute to reactions that form amino acids under the right conditions. If interstellar objects carry different chemical packages, then different planetary systems may receive different starting materials. The early chemistry of life could depend, in part, on which interstellar visitors happen to pass through. Some researchers have taken this idea further, suggesting that interstellar objects could carry not just organic precursors, but dormant biological material. Whether that is plausible remains an open question. What is clear is that complex organic molecules can survive the journey between stars. Whatever was frozen into 3I Atlas billions of years ago has endured extreme isolation and is now being released into our solar neighborhood. The paradox of methanol is not only about quantity, it is about meaning. Methanol is toxic to humans, yet it can also play a role in building biological molecules. It is both harmful and potentially constructive, depending on context. 3I Atlas is releasing tens of kilograms of this substance every second as it races through the inner solar system. That material will disperse, mix with the solar wind, and eventually fade into the background. A few molecules may drift into planetary atmospheres, silent messengers from another star. As 3I Atlas continues its journey away from the Sun, its chemistry will keep changing. Outgassing rates will shift. Molecular ratios may evolve. Some species may disappear while others emerge. Each observation captures only a moment in a longer transformation. We are watching chemistry resume after billions of years of dormancy. As ancient ice meets solar radiation for the first time, the methanol paradox connects stellar birth, interstellar travel, and the possibility of life into a single story. It reminds us that comets are not inert debris, but active participants in the movement of matter through the galaxy. And as we turn from chemical measurements to the latest images captured by our space telescopes, it becomes clear that the surprises are not limited to spectra and ratios. In those images, something looks different. Something that does not fit neatly into expectation. What Hubble recorded next was not anticipated. Hubble has been tracking 3I Atlas since shortly after it was found, giving scientists a consistent visual record over time. On July 21, 2025, Hubble captured its first image of the interstellar object using Wide Field Camera 3. At that stage, the comet was still inbound, moving toward the Sun. The image looked broadly familiar. A soft, fuzzy coma surrounded a central point that remained unresolved, meaning the nucleus itself could not be seen as a solid body. In the background, stars appeared as streaks, not because the stars were moving, but because Hubble was tracking the comet's motion across the sky. At first glance, the structure appeared normal, but one detail stood out. The coma had a teardrop shape that seemed to extend toward the Sun, not away from it. That matters because the most common visual rule of comets is directional. When a comet becomes active, the Sun pushes. Sunlight and the solar wind apply pressure to the released material. Gas and dust stream outward, and the comet's tails point away from the Sun regardless of the comet's direction of travel. This always away from the Sun behavior is one of the most reliable patterns in comet astronomy. The July Hubble image did not show a classic tail, but it did show a sunward extension. This is sometimes described as an anti-tail. The name can be misleading. It does not mean material is being blown toward the Sun. In many cases, it is a viewing effect. Comets can release dust into a wide, flattened fan along their orbit. If Earth happens to view that fan edge-on, part of the dust can appear to point sunward in a two-dimensional image, even though it is not physically moving in that direction. This kind of geometry-driven anti-tail is a known phenomenon, and it often disappears as viewing angles change. That is why the next observation mattered. On November 30th, 2025, Hubble observed 3I Atlas again with the same instrument. By then, the comet had passed perihelion by about a month. It was now outbound, moving away from the Sun and heading toward its later encounter with Jupiter. The geometry of the Sun, comet, and Earth had changed. If the sunward feature in July had been mostly a perspective effect, it should have shifted noticeably or faded. It did not. The new image showed the same basic teardrop coma and the same sunward extension. The morphology looked stubbornly similar. This persistence made the purely geometric explanation less satisfying. Not impossible, but harder to defend with confidence. If the viewpoint changes and the feature stays, the feature may be tied to the object's physical behavior rather than to our line of sight alone. In simple terms, Something about how 3I Atlas is releasing material may be producing a stable asymmetry oriented toward the Sun. Avi Loeb responded quickly to the November image with a hypothesis that goes beyond the usual explanation of dust geometry. He proposed that the sunward structure might reflect large fragments that separated from the comet near perihelion. The idea is straightforward in principle. When a comet heats up, it releases material. Gas leaves the surface, and the nucleus experiences a small reactive push called non-gravitational acceleration. This is normal. Loeb suggested that the ejected material could include not only fine dust and gas, but also larger, more solid chunks. If those chunks are big enough, radiation pressure would have little effect on them. They would not be pushed away like dust. Instead, they would continue along paths close to the comet's orbit. If fragments broke off earlier, they could end up positioned sunward of the nucleus later. Not because they are moving toward the Sun, but because their orbital location is slightly offset. In this picture, the sunward extension in Hubble is not a tail in the usual sense. It is a debris field, a collection of fragments that trail the main nucleus in orbital terms and now appear closer to the Sun along our line of sight. Loeb estimated that if such objects separated near perihelion, the offset could be on the order of tens of thousands of kilometers, roughly matching the scale implied by the November image. The match could be coincidence. It could also be meaningful. The image alone cannot decide. It provides a shape, not a definitive physical map. Most comet scientists remain cautious about this interpretation. Anti-tails are real and can persist longer than expected when dust is distributed in complex ways. A stable sunward feature is unusual, but not unheard of. A debris field is possible, but it is not required to explain the observation. Still, the idea matters because it points to a testable outcome. If the feature is made of solid fragments, then 3I Atlas is fragmenting. It would be losing pieces during its passage. That would be important regardless of whether anyone considers artificial explanations. Fragmentation would mean the comet is not passing through intact. It is shedding material that could remain in the solar system long after the main body leaves. Additional imagery from a spacecraft added another layer. In early November, a European Space Agency spacecraft on its way to Jupiter turned instruments toward 3I Atlas and captured a partial navigation camera view. The spacecraft was tens of millions of miles away from the comet at the time. Most of its higher priority data was scheduled for later downlink, but a small portion of one image was transmitted early. It was low resolution and incomplete, but it still revealed structure. In that partial view, the comet showed a bright central region surrounded by a coma, which was expected. What stood out was the presence of two distinct tails extending in different directions. One tail appeared straighter and more directly aligned away from the Sun. This is consistent with a plasma tail, made of ionized gas swept straight back by the solar wind. The other tail was fainter and followed a different angle, consistent with a dust tail, made of solid particles that follow orbital paths shaped by both gravity and radiation pressure. Two tails are not rare. Many active comets show both. The surprise was not the existence of two tails. It was the level of activity implied by them so soon after perihelion. Earlier ground-based images, taken in early November, had suggested a compact coma and little evidence of a strong tail. Now, this spacecraft image suggested that outgassing and tail formation were still significant. One explanation is that the earlier observations lacked the resolution and sensitivity to reveal faint, extended structure. Another is that the comet's activity was changing rapidly, and the timing of observations captured different states. Either way, the comparison highlights a basic challenge. We can only interpret what we can detect. and different instruments reveal different parts of the same reality. 3I Atlas has been observed in visible light, infrared, ultraviolet, X-rays, and radio bands. Each wavelength highlights different physics. Visible images emphasize dust scattering and coma shape. Infrared spectra reveal molecular gases. Ultraviolet observations trace ionized species. X-rays show the boundary where the solar wind interacts with neutral gas. Radio and millimeter data capture specific molecules and distributed sources. No single view is complete. The overall portrait is assembled from fragments. The imaging record now includes several such fragments that do not fit neatly into a single simple template. A persistent sunward asymmetry in Hubble, dual tail structure, and higher than expected activity in spacecraft imagery. Shifts in tail prominence over time, combined with the color changes and chemical extremes already discussed. These visuals strengthen the impression that 3I Atlas is an outlier. Not because it violates physics, but because it sits at the edge of the range we have learned to expect from solar system comets. Loeb has grouped these features into what he calls anomalies, meaning observations that require extra explanation or careful scrutiny. Critics respond that interstellar comets should be expected to look odd. They formed under different conditions and spent long periods under different radiation environments. Strange behavior is not the same as unnatural origin. Others accept that the natural explanation is strong, but note that it is not proven beyond every doubt. Because the nucleus remains unresolved and key details remain inferred. What matters most in the imaging data is the evolution. From July to November, the comet's appearance has shifted. Brightness has varied. Color has transformed. Tail structure has changed. Activity has risen and fallen in ways that depend on wavelength, instrument, and timing. This is not a static object. It is a small body reacting to a new environment in real time. The images also reinforce scale. The nucleus may be as small as a few hundred meters across or as large as several kilometers. Either way, it is tiny compared to planets. Tiny even compared to many large asteroids. Yet it has traveled for an extraordinary length of time through interstellar space and is now recorded as a pattern of pixels by instruments that can measure details far beyond what earlier generations of astronomers could imagine. December 19th will provide the best imaging opportunity of this passage. The comet will be at its closest approach to Earth, and the new moon will allow darker skies for ground-based telescopes. Both space-based and ground-based instruments will be able to capture higher quality data than at most other times in the approach. Those images may clarify whether the sunward feature is simply dust geometry, whether fragmentation is occurring, and how active the nucleus truly is on the outbound leg. But images do not interpret themselves. They require context, comparison, and careful modeling. As attention shifts from what 3I Atlas looks like to where it is going, one topic becomes especially controversial: the precision of its trajectory near Jupiter. In mid-March of 2026, 3I Atlas will pass by Jupiter. Close approaches to Jupiter are not rare. The planet's gravity shapes the paths of many passing objects. What has drawn debate is the predicted distance of this approach and how that distance relates to a specific gravitational boundary. Every planet has a region of space where its gravity dominates over the sun's pull. This region is called the Hill sphere. Inside that region, an object can orbit the planet more easily. Outside it, the sun dominates, and objects follow paths centered on the sun. The edge of that region is described by the Hill radius, the boundary between the planet's gravitational territory and the sun's broader control. For Jupiter, that boundary depends on Jupiter's distance from the sun, which changes slightly along Jupiter's orbit. On March 16, 2026, 3I Atlas is predicted to make its closest pass by Jupiter. At that time, Jupiter will be about 784 million kilometers from the Sun. Using that distance in the standard hill sphere calculation gives a hill radius of about 53.502 million kilometers. This is not a physical shell or a hard edge. It is a useful boundary used in orbital mechanics. Inside it, Jupiter's gravity is strong enough that moons and temporary captured objects can remain bound more easily. Outside it, the Sun's gravity dominates more strongly. This is where the numbers start to attract attention. NASA's Jet Propulsion Laboratory maintains an ephemeris system called Horizons that predicts the positions of solar system bodies. It uses observations from many telescopes to refine trajectories. And it also accounts for small non-gravitational forces. For comets, the main non-gravitational effect is outgassing. Gas leaving the nucleus can act like a tiny thruster, producing a measurable change in the orbit. For 3I Atlas, that outgassing push was detected near perihelion and incorporated into the model. Based on the latest Horizon solution, the predicted minimum distance between 3I Atlas and Jupiter is about 53.445 million kilometers. When you compare that to the hill radius value of 53.502 million kilometers, the difference is less than 60,000 kilometers. That is a small fraction of the total. It means the object is predicted to skim the edge of Jupiter's gravitational influence zone with a precision that feels surprising. Avi Loeb has taken this proximity and asked a probability question. If you imagine a range of possible outbound paths consistent with observational uncertainty, and then ask how often a path would land so close to Jupiter's hill radius, you can compute a number. His estimate is on the order of 1 chance in 26,000. In other words, if the trajectory were effectively random within a certain band, the odds of it grazing that specific boundary would be low. Not impossible, but uncommon. That probability estimate is one of the reasons this topic has become controversial. Loeb argues that such precision could be consistent with a controlled adjustment. He suggests that the non-gravitational acceleration measured near perihelion might not have been purely natural outgassing, but a purposeful course correction. In that scenario, the object would not be a comet in the ordinary sense. It would be a technological artifact using a small push to tune its path. It is important to keep the claim in its actual form. Loeb does not state that 3I Atlas is definitely artificial. He assigns a probability in the range of 30 to 40% based on what he considers an accumulation of unusual features. He treats the Jupiter geometry as one piece of a larger pattern, and he calls for continued observation rather than certainty. Most planetary scientists reject this framing. Their objections begin with the probability calculation itself. The 1 in 26,000 estimate depends heavily on assumptions about what counts as a random trajectory and how the uncertainty band is defined. The path of an interstellar object is not drawn from a uniform distribution of all possible paths. It is produced by gravity, initial conditions far outside the solar system, and perturbations that occur as it moves inward. Some approaches are more likely than others. The random model used in the estimate may not match the real physics that selects which paths occur. They also point out that non-gravitational acceleration is normal for comets. When sunlight heats an uneven surface, jets can turn on and off. The direction and strength of the resulting thrust can change as the nucleus rotates. This can produce small pushes in specific directions without any control system. The measured acceleration in 3I Atlas can be explained by ordinary outgassing, and its magnitude does not require any artificial mechanism. There is a deeper point behind this skepticism. The hill radius is a mathematical tool, not a physical target. Nature does not recognize that number as a special place. Jupiter does not have a wall at 53 million kilometers. The transition from Jupiter-dominated dynamics to Sun-dominated dynamics is gradual. Passing just inside versus just outside that boundary does not suddenly flip the physics. The forces change smoothly with distance. The Hill radius is useful for classification, but it is not a sharp line carved into space. This is why some scientists argue that focusing on the Hill radius as a bullseye is misleading. If the predicted closest approach were 50 million kilometers or 60 million kilometers, would the passage be fundamentally less interesting? Jupiter's gravity would still matter, and the object's trajectory would still be altered. The Hill radius makes a clean number for discussion, but the object's experience of gravity does not change abruptly at that edge. Loeb's view is different because he treats the Hill sphere boundary as operationally meaningful. If an object wanted to deploy devices into stable Jupiter orbits, those devices would need to end up inside the region where Jupiter can hold them. If a civilization wanted low-energy insertion points, it might take advantage of stable gravitational regions near Jupiter, including areas related to Jupiter's Lagrange points. These are locations where gravitational and orbital forces balance in a way that can allow objects to remain in predictable configurations. Loeb argues that, in that context, a path that grazes the Hill boundary could be interpreted as intentional positioning. He extends the speculation further. In his scenario, 3I Atlas could release objects as it passes Jupiter. Those objects would then need to reduce their speed relative to Jupiter to be captured. The relative velocity is high, on the order of dozens of kilometers per second, which would require a major propulsion effort. That would be difficult for current human technology. But Loeb notes that this argument depends on unknown capabilities if the origin were extraterrestrial. From the mainstream perspective, this chain of reasoning adds too many unverified steps. It begins with a probability estimate whose assumptions are disputed, treats a mathematical boundary as a special target, and then builds a narrative of deployment and capture that has no direct evidence. Critics argue that the odds of a mothership interpretation are not 30 to 40%, but extremely small, and that what appears as a cluster of anomalies is better understood as natural variation in a category where normal is not yet well defined. Both sides are working with the same limited reality. The nucleus is unresolved. Outgassing is inferred from its effects. The Jupiter encounter has not happened yet. For now, the data support a natural comet interpretation, but they also leave room for debate because we have so few interstellar examples to compare against. What can be said with confidence is narrow but solid. 3I Atlas is on a path that will take it unusually close to a gravitational boundary defined for Jupiter. Whether that closeness is meaningful depends on what assumptions you bring to the table. Under a natural comet assumption, it is a curious geometry shaped by initial conditions and perturbations. Under a technological assumption, it could be interpreted as an intentional flyby designed to reach a useful region near Jupiter. The same numbers can support different stories because the stories depend on prior beliefs about what is possible. The March 2026 passage is still months away. When it occurs, telescopes will monitor the event. Any sudden changes in brightness, unexpected fragmentation, or unusual acceleration will be measured as carefully as possible. If the object behaves like a normal comet passing through Jupiter's environment, that will strengthen the natural explanation. If it shows something that cannot be accounted for by outgassing and gravity alone, it will force a deeper reassessment. Until then, what remains is the uncomfortable part of science: ambiguity. We keep collecting measurements. We refine models. We argue about assumptions. Gravity and momentum trace the path. But interpretation remains open. As 3I Atlas approaches its closest point to Earth, there is another thread that intersects with this debate in a different way. It is not about where the object is going, but about what it is releasing. The molecules detected in its coma are not just markers of formation environment. They also connect to a larger question about life. Where did life come from? And could objects like this move key ingredients from one star system to another? The chemical list already discussed includes methanol, hydrogen cyanide, carbon dioxide, and water. Each of these compounds has a role in prebiotic chemistry under certain conditions. They can support pathways that build more complex organics. They can also be harmful in other contexts. The same chemistry can point toward creation or toward destruction, depending on where it lands and what environment receives it. Panspermia is one of the oldest ideas ever proposed to explain the origin of life. The word comes from Greek and roughly means seeds everywhere. In its modern scientific form, the hypothesis suggests that life, or at least the molecular precursors of life, may be spread throughout the cosmos by comets, asteroids, and interstellar objects. Instead of life emerging independently on every planet, biology across the universe might share common chemical roots, distributed over immense distances and long periods of time. This idea is not as speculative as it may sound at first. Astronomers and chemists have repeatedly shown that organic molecules are widespread in space. Amino acids have been found in meteorites that landed on Earth. Complex carbon-based molecules have been detected in interstellar clouds, in regions where stars are forming, and in the material expelled by dying stars. The raw ingredients of life appear to be abundant. What remains uncertain is whether those ingredients can assemble into living systems, and whether they can survive the harsh journey between stars. 3I Atlas has renewed attention on panspermia because of what it is releasing. Observations have shown unusually high levels of methanol and hydrogen cyanide in its coma. Both molecules are considered important in prebiotic chemistry. Both can participate in reaction pathways that lead from simple compounds to more complex biological molecules. Methanol is a simple alcohol composed of one carbon atom, one oxygen atom, and 4 hydrogen atoms. Under the right conditions, methanol can be transformed into formaldehyde, another key molecule in prebiotic chemistry. Formaldehyde can then take part in reactions that produce sugars, including ribose. Ribose is a central component of ribonucleic acid, or RNA. This chain of reactions forms part of what is known as the RNA world hypothesis, the idea that early life relied on RNA-like molecules before the emergence of DNA and proteins. In that framework, methanol sits near the beginning of a possible chemical pathway toward genetic systems. Hydrogen cyanide is even more directly tied to the chemistry of life. Under suitable conditions, hydrogen cyanide molecules can react with each other to form adenine. Adenine is one of the 4 nucleic acid bases used in both DNA and RNA. It is a fundamental letter in the genetic alphabet. The discovery that adenine can form from hydrogen cyanide through purely chemical reactions was a major milestone in prebiotic chemistry. It showed that essential components of genetic material could arise without biology, given the right environment. When scientists measured high production rates of both methanol and hydrogen cyanide in 3I Atlas, the panspermia hypothesis gained new relevance. Here was an interstellar object carrying precisely the kinds of molecules that laboratory experiments have shown can lead toward life-related chemistry. If similar objects struck the early Earth, they could have delivered materials that helped push chemistry toward biology. In that sense, 3I Atlas may resemble the kinds of visitors that once influenced our own planet's history. Avi Loeb has embraced this interpretation openly. He has described 3I Atlas as a kind of interstellar gardener, spreading chemical seeds as it travels from star system to star system. From this perspective, the comet is not merely passing through space, but distributing compounds that could fertilize young worlds under the right conditions. But the story does not end on a hopeful note. Hydrogen cyanide is not only a building block of life, it is also one of the most potent poisons known. It interferes with cellular respiration by preventing cells from using oxygen. In humans and many other organisms, even small doses can be fatal within minutes. Hydrogen cyanide has appeared repeatedly in human history as a weapon and a means of execution. The same molecule that can help create life can also destroy it efficiently. This dual nature is not unique. Many molecules involved in prebiotic chemistry are dangerous to modern life. Formaldehyde is a carcinogen. Methanol can cause blindness and death if ingested. The chemistry associated with life's origins overlaps with the chemistry of toxicity. Whether a molecule contributes to creation or destruction depends on concentration, environment, and timing. Loeb has explored this darker implication as well. He has speculated about the idea of interstellar objects acting as distributors of lethal chemistry, not out of intent, but through indifference. In this view, some interstellar visitors might sterilize worlds rather than seed them. A planet with an existing oxygen-breathing biosphere could suffer catastrophic damage if exposed to large amounts of toxic compounds. In contrast, a lifeless planet might benefit from the same delivery, using those molecules to build complexity from scratch. From this perspective, the universe does not favor life or oppose it. It simply supplies ingredients. What happens next depends on local conditions. The same chemical payload can have radically different outcomes on different worlds. A young, lifeless Earth 4 billion years ago may have been an ideal recipient for reactive molecules like hydrogen cyanide. There were no ecosystems to poison, no oxygen-dependent organisms to kill. The chemistry could proceed toward complexity without immediate harm. On a planet where life has already emerged, the outcome could be very different. Toxic effects would dominate before any creative chemistry had a chance to act. Cells would die, ecosystems would collapse, and the same molecules that once helped spark life elsewhere would become agents of destruction. The difference lies not in the molecules themselves, but in the biological state of the planet they encounter. 3I Atlas carries the same chemical payload regardless of destination. Whether that payload acts as seed or poison is determined entirely by context. This ambiguity is unsettling but also revealing. It suggests that the universe is not designed with biology in mind. It is a vast chemical environment where outcomes vary widely based on chance and circumstance. The tens of kilograms of methanol released every second by 3I Atlas will disperse into the solar system. Some fraction may eventually intersect planetary environments, Mars, the moons of Jupiter, and other bodies could receive trace amounts. A tiny number of molecules might even reach Earth's upper atmosphere, though the quantities would be extremely small. Over billions of years, this kind of delivery has likely happened many times. Comets, interstellar objects, and dust grains have continuously exchanged material with planets. The origin of life on Earth remains unresolved. Despite decades of research, there is no consensus on how chemistry crossed the threshold into biology. What is clear is that organic molecules were present, both from local processes and from material delivered from space. 3I Atlas adds a new dimension to that picture. It shows that interstellar chemistry may be more diverse than we assumed. Objects from other star systems may carry different molecular mixtures than those formed near our Sun. If many such objects passed through the early solar system, they could have influenced the available chemistry in subtle ways. The particular mix of compounds present at key moments might have shaped the path of prebiotic evolution. This remains speculation, We cannot test whether 3I Atlas or similar objects contributed directly to life on Earth. The timescales are too long and the evidence too diffuse. But the idea is consistent with what we observe. The molecules exist. The delivery mechanism exists. The possibility cannot be dismissed outright. What makes 3I Atlas important is not simply that it carries organic molecules. Many comets do. What makes it important is that we can study it in detail. We can measure production rates, track how chemistry changes with solar heating, and compare its composition to that of solar system comets. In doing so, we gain insight into the range of chemical environments that exist beyond our star. The seeds are moving. Tens of kilograms of methanol each second, fractions of a kilogram of hydrogen cyanide each second, carbon dioxide, water, and many other compounds joining the cosmic flow. Whether those seeds nurture life or extinguish it is not a question the comet can answer. It simply delivers. The universe provides. The outcome depends on conditions that vary from world to world. As 3I Atlas approaches its closest encounter with Earth, the scientific community is preparing intensely. Observatories across the globe are coordinating observations. Space telescopes are adjusting schedules. Researchers are readying themselves for a surge of new data. Among them are scientists who insist that open-mindedness is not weakness, but a necessary part of confronting the unknown. Scientists who believe that looking away from uncomfortable questions is more dangerous than asking them. And they are watching closely. Since the discovery of 3I Atlas, a quieter conflict has unfolded alongside the flood of observations. It has not been a dispute over measurements or raw data. The data are public, shared, and continuously updated. The conflict has been about interpretation, about which questions are considered reasonable to ask, and which ideas are dismissed before they are fully examined. On one side of this divide are planetary scientists who have spent their careers studying comets, asteroids, and the debris left behind by planetary formation. They have seen strange objects before. They have watched anomalies emerge and then dissolve as more data arrived. From their perspective, 3I Atlas is unusual but not extraordinary. It is an interstellar comet with unfamiliar chemistry, shaped by a history outside our solar system, valuable, fascinating, and worth studying in detail. But still a natural object governed by known physical processes. On the other side is Avi Loeb and a small number of researchers who argue that the search for extraterrestrial technology should be treated as a legitimate scientific question. They do not claim certainty. They argue that ruling out the technological hypothesis too quickly reflects bias rather than skepticism. In their view, the accumulated peculiarities of 3I Atlas justify closer scrutiny. Not belief, but attention. Not conclusions, but openness. This tension did not begin with 3I Atlas. It traces back to the first known interstellar visitor detected in 2017. That object displayed properties that defied easy explanation. Its elongated shape, the absence of a clear coma, and its apparent acceleration as it left the solar system sparked debate. Loeb proposed that it might have been a solar sail, a thin artificial structure pushed by sunlight. Most astronomers rejected that idea and offered natural explanations involving unusual shapes or surface properties. The disagreement never fully resolved. Instead, it set a precedent. 3I Atlas reopened that debate under different conditions. Unlike the earlier visitor, this object clearly outgasses. It has a coma. It behaves like a comet in many respects. These facts strongly support a natural interpretation. At the same time, its chemistry is extreme. Its trajectory has features that attract attention, and its visual behavior has included structures that do not align neatly with simple models. For those inclined to consider alternatives, these features keep the technological question alive. Jason Wright has become one of the most prominent critics of Loeb's approach. He has examined each proposed anomaly in detail and argued that none require exotic explanations. Unusual chemistry is expected from an object formed around another star. A close pass near Jupiter's Hill boundary can arise naturally from orbital dynamics. Persistent sunward features can be produced by complex dust distributions and viewing geometry. Wright's point is not that the natural explanations are proven beyond doubt, but that they exist. If each anomaly can be explained without invoking technology, then the collection of anomalies does not constitute evidence for technology. Loeb responds that this approach applies unequal standards. Natural explanations, he argues, are accepted with modest evidence, while technological explanations are dismissed unless they meet an almost unreachable threshold. He does not deny that extraordinary claims require strong evidence. He argues that refusing to even consider such claims is a different problem. In his view, skepticism should cut both ways. There is truth on both sides. Science does rely on prior probability. Claims that would overturn large parts of our understanding rightly face a higher evidentiary bar. This is not prejudice. It is statistical reasoning. At the same time, history shows that expertise can sometimes harden into resistance. Ideas that later proved correct were once ridiculed or ignored. The balance between caution and openness is difficult, and it must be recalibrated repeatedly as new data emerge. The stakes in this case amplify that tension. If 3I Atlas were confirmed to be technological in origin, the implications would be unprecedented. It would mean that intelligence has arisen elsewhere, that technology can traverse interstellar space, and that we are not alone. Such a discovery would reshape science, philosophy, and society, precisely because the consequences would be so profound. The risk of wishful thinking is high. The desire for meaning can distort judgment. The history of the search for extraterrestrial intelligence contains many false alarms, signals that appeared artificial until mundane explanations emerged. Loeb is aware of this history. He has stated repeatedly that he does not claim certainty. He assigns a probability in the range of 30 to 40% to the technological hypothesis, based on what he views as cumulative evidence. He calls for more observations, not conclusions. His critics argue that even framing the question this way fuels misunderstanding. When the public hears that a prominent scientist considers alien technology plausible, the nuance is often lost. Probabilities are flattened into headlines. Caveats disappear. Public discussion of 3I Atlas has grown rapidly. Social media has amplified the most provocative interpretations. Posts about alien spacecraft and hidden intentions spread more widely than careful explanations of cometary physics. This is not unique to this case. It reflects how modern information ecosystems reward novelty and drama over restraint. Once speculative ideas leave the academic context, they evolve in unpredictable ways. Loeb argues that this is not a reason to remain silent. Science, in his view, should not retreat behind closed doors. The public deserves to know what questions scientists are asking, even when those questions are uncomfortable or speculative. Transparency, he believes, is more important than controlling narratives. There is integrity in this position, even if it underestimates how easily nuance can be lost. The institutional response has been mixed. Some colleagues respect Loeb's willingness to challenge convention. Others worry that his public framing undermines the credibility of the field. Labels have been applied at both extremes: visionary and irresponsible. often oversimplifying a more complex reality. He is a capable scientist with unconventional ideas, operating in a media environment that magnifies both insight and error. Meanwhile, the observations continue. X-ray measurements, infrared spectra, radio detections, optical imaging. Each dataset adds detail without settling the larger debate. The eventual conclusions will rest on this evidence, not on personalities or public arguments. Nature does not respond to speculation. It responds to measurement. December 19th approaches, the peak of this observational campaign. After that, 3I Atlas will recede. Its brightness will fade. Its signals will weaken. By the time it reaches Jupiter in March, our ability to extract new information may be limited. The window is narrow and closing. Across the debate, there is one common thread: curiosity. Whether they view 3I Atlas as an unusual comet or something that warrants more radical questions, the scientists watching it share a commitment to understanding. They are collecting every usable photon, testing every model, arguing not out of hostility, but out of engagement. This is what science looks like at its edge. An object arrives from beyond our star system. It does not offer clear answers. It offers data, ambiguity, and the chance to learn. Observations continue. Hypotheses compete. Imagination flickers and is reined back by caution. 3I Atlas keeps moving, and somewhere between what we can measure and what we wonder lies the truth, waiting to be approached. Never fully grasped, but pursued nonetheless. Project forward a few months. The northern hemisphere will be moving toward spring. Days will start to stretch out again. The pressure and noise of the holiday season will be behind us. And then, on March 16th, 2026, 3I Atlas reaches its closest point to Jupiter. The predicted distance is about 53.4 million kilometers from the largest planet in our solar system. So close to Jupiter's hill boundary that the gap is smaller than what most people imagine when they hear the word distance. By then, the interstellar object will still be moving far too fast to be captured. About 65 kilometers per second relative to Jupiter. It will not slow down and settle in. It will not linger. It will be a flyby, brief and clean, followed by a long departure into interstellar space. What happens that day is, honestly, unknown. The most likely outcome is that nothing unusual occurs. Jupiter's gravity bends the path slightly, as it does for countless natural objects. And 3I Atlas continues outward. No braking, no maneuvering, no sudden change in course, no release of anything into Jovian orbit. Just an object obeying gravity, momentum, and whatever small outgassing forces remain as it cools and fades. But the reason people keep talking about March is that a low probability alternative exists. A remote possibility that the close approach is not just an interesting geometry, a possibility that what looks like coincidence could line up with something more intentional. Most researchers do not expect that outcome. Even many who find the Jupiter geometry striking still expect a normal cometary pass. But not expected is not the same as impossible. And that is why the event will be watched. One practical suggestion that keeps returning is simple after the flyby. Look for new objects near Jupiter. The idea is not to assume anything, but to check. If 3I Atlas were somehow releasing devices, the signature would be clear. In principle, new objects appearing in Jupiter's neighborhood that were not previously tracked, not consistent with known debris, and not attributable to normal processes. The probability of that is extremely low. Still, the search itself is not expensive. Surveys of Jupiter's environment happen anyway. Looking for changes is part of how planetary science works, even if there is no spacecraft positioned to scrutinize the moment in real time. Telescopes on and around Earth can still track the comet's brightness, its tail structure, and any unexpected changes in motion. If something dramatic occurs, it would not stay hidden. It would appear as a measurable deviation, a sudden acceleration inconsistent with outgassing, an abrupt shift in direction, or new bodies that persist in the Jovian system. If nothing appears, then nothing is lost. What remains is a better measured orbit and a better understood comet. That is the deeper pattern here. In science, you look even when you expect to find nothing, because sometimes the act of looking is what separates a confident assumption from a tested conclusion. Most searches confirm the ordinary. A few reveal something new. Both outcomes matter. After the Jupiter flyby, the story continues in a quieter form. Data processing, model refinement, paper after paper. Observations from the December close pass by Earth will take months, and in some cases years, to fully analyze. Some puzzles that feel sharp right now may soften as calibration improves and more comparisons become available. Some may remain stubborn. Chemistry that looks extreme might become understandable once the full set of volatile species is modeled together. Or it may remain a genuine outlier, a data point that forces new categories. Follow-up observations also matter because comets change as they recede. If carbon dioxide dominated early, does that dominance persist as the sun's influence weakens? Does water become relatively more visible later? Or does the object simply go quiet before that shift can be measured? Does methanol production fall smoothly? Or does it turn off in steps as different regions stop receiving enough heat, as fresh layers are exposed and then refreeze? Does the coma chemistry evolve in a predictable way? Or does it keep surprising us? Radio telescopes will likely continue targeted listening, not because silence proves anything, but because it is easy to check. A lack of detected signals does not prove the absence of technology. It only proves that no signal was detected by the instruments. In the frequencies, sensitivities, and time windows that were used. That distinction sounds small, but it matters. Detection is a technical event with limits. Non-detection is not the same as a clean conclusion. In parallel, researchers will keep stepping back to the bigger view. 3 interstellar objects within less than a decade. The first was strange and brief. The second looked more like a conventional comet. The third combines familiar comet behavior with extreme chemistry and confusing morphology. The sample size is still small, but it is no longer one-off. With 3 examples, comparisons become more meaningful. Patterns might begin to emerge, or we may find that diversity is the only consistent theme. This is part of a broader shift in how we relate to the solar system. For most of human history, the sky seemed like a closed neighborhood. Planets, moons, and local comets that return on predictable schedules. One system, one set of rules we could test again and again. Interstellar visitors change that. They are pieces of other systems crossing ours. They carry chemistry formed under different conditions. They bring histories we did not witness. And they force us to admit something basic. We have been building our definitions of normal from a single example. That isolation is ending, not because we can travel to other stars, but because pieces of other stars are coming to us. And the pace is likely to increase. Wide-field surveys are becoming more powerful and more continuous. The Vera C. Rubin Observatory, built to scan the southern sky repeatedly and deeply, is designed for exactly this kind of discovery. As survey capability grows, faint and fast-moving objects that once slipped by unnoticed will be found earlier and tracked longer. The trickle of interstellar visitors could become a steady stream, not one object every few years, but potentially many candidates over a decade. And eventually more as detection pipelines mature. If that happens, then 3I Atlas becomes something more than a single mystery. It becomes a preview of a new era, an era where interstellar object is not a once-in-a-generation headline but a category with a growing dataset. With enough examples, the debate over what counts as normal will become less philosophical and more statistical. We will learn the typical chemical profiles, the range of outgassing behaviors, the common shapes of comas, and the frequency of rare features like persistent sunward asymmetry. Some anomalies will stop being anomalies. Others will stand out more clearly against a better defined baseline. And somewhere among future objects, there may be one that truly breaks the framework. Not one that is merely rare, but one that cannot be explained by outgassing, dust physics, and orbital mechanics. Even after careful work, that day could arrive in 10 years, in 100 years, or it may never arrive. There is no way to know without building the habit of looking. That is why the questions raised by 3I Atlas matter, even if the final answer is ordinary. They connect directly to the deepest scientific uncertainties people carry, whether they speak them out loud or not. Where did we come from? How common is life? How common is intelligence? Are we alone? These are not only philosophical questions. Parts of them can be tested. Observations can constrain them. Data can narrow what is plausible even when it cannot deliver certainty, so the focus remains practical. Gather the measurements while the object is bright enough to study. Track changes as it recedes. Watch the Jupiter flyby for any measurable deviations. Compare the chemistry against known comets and against future interstellar visitors. Let the picture assemble slowly, piece by piece, without forcing it into a conclusion too early. The window is finite. 3I Atlas will fade as it moves outward. By the time it reaches Jupiter, the limits of our instruments will be closer than most people realize. After that, it continues into the dark between stars, taking its secrets with it. What stays behind is not a fragment of the object, but a record spectra, images, light curves, orbital solutions, and the questions those datasets produce. And that is what unites the people watching most closely. Regardless of which interpretation they favor, curiosity strong enough to stay with the evidence, even when the evidence refuses to give a clean answer. The scientists who refuse to look away